Hello guys. So we are going to do notes 30, which is writing skeleton equations. You can see that it's kind of short, but it does take a little while putting everything together. It's using stuff from what we did before break of going from names to formula writing, and then putting that into a chemical equation to figure out what kind of reaction it is. And here we go. All right. So, first off, there is something pretty important we have to remember. There's these things called diatomic elements. Now, if you remember from our naming unit, di means two. So that's just what the prefix means, diatomic elements. So they're elements which exist in their free state only in pairs, meaning you are not going to find these elements anywhere on the planet except in pairs or in a compound with something else. You're never going to find them floating around by themselves. There's only 7 elements that do this that are always found in pairs. They are these ones down below. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all come in pairs. So anytime you see one of these elements in a chemical equation like this, you know when I'm writing their symbols down below. So here's one right here. Here's chlorine, right? So that's chlorine. I'm never going to write chlorine by itself in my chemical equation. I would never do that because chlorine isn't by itself. We're talking about a real life reaction right here. And in real life, chlorine always comes in pairs. So if it always comes in pairs, I'm always going to add a little 2 there because that's how chlorine is found. So if hydrogen, there's actually no. So if hydrogen is also up here, hydrogen is also always found in pairs. So I would not write it by itself. So when hydrogen comes into contact with chlorine and possibly reacts with this hydrogen chloride, they always react in pairs because that's just how they're found in nature. So when you have to remember these 7 elements, when you're writing these chemical equations, we're going from name to formulas. And if you see one of those 7 elements, they always have a 2. That's just, they have a 2 because they're one of those 7 elements that are always diatomic. They're always found in pairs. A way to kind of help you remember those 7, I have my periodic table here. Let me click on it. Not letting me. So I gotta go back over here. So over here, the 7 elements are kind of grouped together and they actually make the shape of the 7. So they're, except for hydrogen. So we have hydrogen, and it's these. We have nitrogen, oxygen, fluorine, bromine, iodine. See how they look like a 7? Nitrogen, oxygen, chlorine, bromine, iodine, and then hydrogen, which kind of just is over there. But it's hydrogen, and then the 7 keeps like writing above it. So those 7 elements, all of those have a 2. So if you wanted to, on that periodic table that we've been working on, I'm going to have the kids do this in class. We're going to add either a little 2 up here. It's not right in the right spot. So add a little 2 like in their top corner, reminding you that they always come in 2s. Or you could even write like N2. That's not looking good. I don't know why it doesn't let me write on PDFs very well. But an N2 like that, you could write that in the corner of nitrogen. Let me erase this. So maybe we could make it look a little neater. I don't think I can because the board just doesn't let me anymore. But you could put that should be H2. But you could actually write that in the corner, or you could draw like a pair, symbols like that, so that element always comes in pairs. But just something, put something on your periodic table that we've been filling in throughout the year to help you remember that those are our 7 diatomic elements. Because if you remember those 7, it just makes writing equations a lot easier. You don't have to look at your notes every time to remember those 7. Hopefully you'll also just start recognizing them. Okay, and then lastly, before we start writing these equations, is that if I say a skeleton equation, what I mean is it's unbalanced. So we're writing unbalanced equations, and I'll show you what that means in a second. We're going to learn about balancing tomorrow, okay? So we're gonna learn how to balance them very quickly. But to start, we're just writing skeleton equations. That's why it says writing skeleton equations, which is just going from their name to writing their formulas, which I had already started, H2 plus Cl2. And now we're going to figure out hydrogen chloride, how to name it. But how all you have to do to be able to write these things down is to remember our naming skills. Okay, so we're going to go back and try to remember our naming skills. Now, hydrogen and chlorine. So we have this hydrogen chloride. How do I know if I'm going to be using my ionic naming, which has Roman numerals and charges that I crisscross to figure out their symbols, or if it's molecular? So remember, molecular is when I use prefixes like di, tri, hepta, nana. Molecular is with a non-metal with another non-metal, and ionic is with a metal with a non-metal. So when I look at hydrogen and chloride, hydrogen is a non-metal and chlorine is a non-metal on the periodic table. So those are both non-metals and it's molecular. So then I just use their prefixes to tell me how many of each one there are. Well, there is no prefixes. There isn't one on either one of them. There isn't one in front of hydrogen. There isn't one in front of chlorine. So that means there's just one of them. So I have HCl, like that. You could also have done the charges. So this is actually an acid, which we haven't really learned about acids. And so I was trying to kind of avoid it. But acids, you really would cross the charges as well. But either way, they're 1-to-1 and they would balance to HCl. So HCl is what the compound is. Okay, so we have it wrote out. Now, if you notice what I said unbalanced before, we're going to leave it like this today, but we're going to not leave it like this tomorrow. So how do I know it's unbalanced? See how on this side I have 2 hydrogens on this side of the arrow? So I'm saying I have 2 hydrogens that meet 2 chlorines and they make 1 hydrogen and 1 chlorine. That's not possible. We didn't magically lose 1 hydrogen and 1 chlorine. That doesn't happen in real life. In real life, we'd have to have the same amount of stuff on this side of the arrow as we have on this side of the arrow. They have to match. That's the law of conservation of mass. But for right now, we're okay with it. Right now, we're writing skeleton equations, and we're not going to balance them. We're just going to write their names. So this is a skeleton equation. It's not balanced, but it is what is happening. H2 will meet Cl2, and they will make some number of HCl. All right, now what type of reaction is that? We have 2 little things that make 1 bigger product. So more than 1 reactant, only 1 product. They all come together to make 1 bigger product. That is a addition reaction. Notice that sometimes it's also called synthesis reaction. And sometimes, like in our assignment that I forgot to change and try to fix later, it could also be called combination reaction. So all those names work. This is the name that I'm going to use on tests and quizzes, is the addition reaction. But just know that those other 2 exist, and sometimes they pop up on, like, we use a virtual assignment, something like that. Another kind of teacher might use one of the other names. Oh, let me scroll down. Okay, now that we kind of know what we're doing, I'm going to try to speed up a little bit. Because we only have 4 left. Try to get those done. All right. So same thing. We're just using our naming skills that we did before to write down their formulas down here, but then tell me what kind of reaction that is. So before, if you see these Roman numerals, well, then you automatically know that Roman numeral means iron's charge. It's telling you that this is a +3. So if there's already a charge in the name, then I know that this is the kind that I write their charges above them and crisscross the numbers down to get their subscripts. So I know that iron symbol is Fe. I know that oxygen symbol is O. But now I want to figure out their numbers here. So remember back from naming, before break, you write their charges above them. Iron is a +3, because Roman numeral said it was. Oxygen, I look on the periodic table from the things we've had labeled forever and ever, and oxygen is in the -2 column. So that's its charge. If +3 and -2 do not equal 0, which they don't, then I have to switch the numbers down or crisscross the charges to get their subscripts. So the 2 comes to the iron, and the 3 comes to the oxygen. And there we go. That is what iron 3 oxide's chemical formula is, Fe2O3. Then I draw my arrow, just as it has there, because they're saying this FeO3 reacts, something is added to it, maybe heat, maybe some kind of catalyst, but it's going to react, and it's going to turn into iron by itself, which is Fe, and oxygen. Now, when you have elements by themselves, easier because I didn't have to figure out their subscripts. I didn't have to do their charges. I just wrote down their symbols that I looked up on the periodic table. But if you have an element by themselves, so if you have an element alone, then you have to ask yourself the question, is it diatomic? Those diatomic, is it one of those 7 diatomic elements that we just talked about? Because if it is, then it needs a little 2. So I go back up and I look at my diatomic list above, and iron is not diatomic, but oxygen is. So it needs a little 2. Okay, so that's how that comes into play, is that oxygen will always be written as O2. Hydrogen will always be H2. Fluorine will always be F2. Okay, so those things have to have a little 2 or it is incorrect. All right, so now we have our reaction. That is it, we're done. Just need to tell me the type. So this is the exact opposite of the one we just did. Instead of little things adding into one product, we have one reactant that breaks down into 2 products, so more than one product. So we have something breaking down. What we call that kind of reaction is one thing breaking down into pieces is decomposition. So can't spell, position, decomposition. It's looking terrible, but that's what it is, decomposition. All right, next one. Same thing, we're just figuring out their symbols, figuring out the type to the side. So all of these are compounds. So I'm looking at all compounds. I don't have any single elements. Most of the time, you're going to be dealing with ionic reactions, which means you write their charges above them and crisscross them to get their symbols. The only time that they're not going to have ionic is when they're going to have prefixes. Like if this said di and that said tri, well, then I would know it was molecular, and I would just use the di, and that means 2, and tri means 3. But being that none of these have prefixes, I know they're all ionic. All of them are going to have to write their charges above them and then crisscross them. All right? So I'll start writing the symbols. Barium is Ba, and chlorine is Cl. I have that much just from looking at the periodic table and seeing what their chemical symbol is. Also on the periodic table, when I look up barium is in the second column, so it has a +2 charge. Chlorine is in the 17th, which has a -1. Those do not balance to 0, so the 1 comes to the barium and the 2 comes to the chlorine. I'm going to write those a little closer together so it looks more like they're actually a compound, which they are, like that. Okay, so that's barium chloride. That is its symbols. It's going to be reacted with, a little plus sign means it's going to be reacted with sodium phosphate. Okay, so sodium symbol is Na. Now, notice phosphate ends in 8, whereas our last one just ended in I, barium chloride. Things that end in I are normal. They are just regular elements on the periodic table that you look up. If it ends in 8 or ite, that is a polyatomic ion. I will repost the polyatomic ion in this set of notes as well if you've lost it, but it wasn't our Unit 5 notes. We're in Unit 6 now. It wasn't your Unit 5 notes. You had your polyatomic ion list on that first page. But anytime you see an H or an I, you still have to go look it up if you don't have it memorized. So phosphate is PO4, and on that polyatomic ion sheet, it tells me phosphate has a -3 charge. Sodium, I look up on the periodic table because it's a regular element, and it's in the first column and has a +1 charge. Those do not balance to 0. There we go. So I do have to crisscross the numbers. So the 3 comes down to the sodium, and the 1 comes down to the phosphate, but I don't have to write 1s. And there we go, balance. Okay, so then I draw my arrow. So these 2 compounds, barium chloride and sodium phosphate, are going to react, and they're going to create 2 different compounds, sodium chloride and barium phosphate. Now, luckily, once you've already done this side, I don't have to look up their charges again because they're the same element. They just reacted and became a different compound. It's still the same element, but they have the same charge. I don't have to look up on the periodic table again. I've already done it. So I'm just going to look at what I did. Over here, sodium had a +1 and chloride had a -1. Well, +1 -1 actually does equal 0. So if it does equal 0, then I just need their symbols, NaCl, which I've already looked up over here. So NaCl, they balance 1 to 1 because I don't have to crisscross their charges down. Done. And it's going to be added with barium phosphate. So over here, barium has a +2, we already looked up, and phosphate had a -3. Those do not balance to 0, so the 3 comes down to the barium, and the 2 comes down to the phosphate. So it'd be barium with a 3. And remember, phosphate is PO4, because polyatomic ion, it is PO4, and that 2 is going to cross down. Now that looks like I have 42 oxygens. I don't want 42 oxygens. I want 2 phosphates. So that's why that parentheses has to come into play. Anytime you have to have more than one polyatomic ion, remember the parentheses have to be there. And there we go. We wrote it all out. Now what kind of reaction is this? I had a compound and a compound created 2 different compounds. So barium and chloride were together over here. Now barium and phosphate are together. On this side, sodium and phosphate are together, but on this side, sodium and chloride are together. So it's 2 compounds that switched partners, or they replaced each other. So that's called a double replacement, because both compounds replace each other. Double replacement reaction. Okay, last one to practice. We have aluminum iodide. So I know the symbol for aluminum is Al. I know the symbol for iodide is I. Now I need the little numbers. So I look at my periodic table, and aluminum always makes a +3. Iodide always makes a -1. Those do not balance to 0, so the 1 comes down to the aluminum, and the 3 comes down to the iodide. Aluminum iodide is going to be reacted with fluorine. Fluorine is an element by itself, so I just write it. But anytime you have an element by itself, you have to ask yourself the question, is it diatomic? So I look at my diatomic list. Fluorine is. Fluorine is a diatomic element, so it needs a 2. If you didn't put it, it would be wrong. So every time you see an element by itself, you have to check your diatomic list. There are 7 diatomic elements, and a lot of times they're the ones that you're dealing with. They're very reactive. Okay, so then we have those are going to be mixed together, and they're going to react to create aluminum fluoride. So that's aluminum and fluoride. I need to write their charges again. So aluminum, we already looked up over here. That's +3. Fluorine, we didn't look up because we didn't have to, because it was by itself. So I'll go look on the periodic table. Fluorine's in the 17th column, has a -1 charge. They don't balance to 0, so the 1 comes down to the aluminum, and the 3 comes down to the fluorine. And lastly, you'll have a leftover iodine by itself. So this is an element by itself. So I just write its symbol. But every time I have an element by itself, I have to ask myself, is it diatomic? If it is, if it's part of my 7 diatomic elements, it needs a little 2, which it does. Iodine is diatomic. It's part of our 7, needs a little 2. Okay, so we have it written out. Now we just have to tell the time. So in this case, I have a compound with an element, with a compound with a different element. So notice how this element kicked out iodine. So fluorine kicks out iodine and makes them all sad and lonely over here and takes its place, aluminum fluoride, in the compound. So when a single element boots out another element and makes it single, that's called a single replacement reaction. Okay, there we go. So really, mostly what we just did, the only thing new that you had to learn today was which ones are diatomic, which ones need those little 2s. The rest of the naming stuff was ionic naming that we already did before break. It's just having to remember it back. Okay,